Dear students, today we would like to discuss about the purpose of root locus. The main purpose of root locus is to find the closed loop system stability by considering open loop transfer function and to find the range of k values for stability, to find the marginal k value and to find the marginal frequency, and whether the given system is having undamped nature or overdamped nature or critically damped or underdamped nature, and to find the relative stability. All these 5 points, all these 5 parameters will be finding with the help of an example. Let us consider open loop transfer function g of s h of s equal to k divided by s into s plus 2. We will be drawing the root locus for the open loop transfer function, and with the help of root locus we will be finding closed loop system stability. Just try to understand. We will be considering open loop transfer function. We will be drawing the root locus for the open loop transfer function. After drawing the root locus for the open loop transfer function, with the help of the root locus we will be able to find the closed loop system stability. You know how to draw the root locus? First, we need to find the number of poles and number of zeros. Here the number of zeros are 0, no zeros are present, and 2 poles are present here. One pole location is at origin, one more pole location is at -2. Here one pole is present at origin and one more pole is present at -2. So find the number of root locus branches. How many 2 poles are there? Always the root locus has to start from pole and has to end at 0. Since we are having 2 poles, the root locus has to start from pole and from this side and here, and it has to end at 0. There are no zeros at all here, so we assume that a 0 is present at infinity somewhere else. And how can we find the root locus is present at a particular point or not? To find the root locus is present at a particular point, to that point, to the right of that point, if the number of poles and number of zeros are odd number, then the root locus is present at that point. Here also, whether root locus is present at this point, how can we find? Here, only if you want to find at this particular point, it is -1.5. Whether the root locus, whether -1.5 is lying on the root locus or not, then to the -1.5, to the right side of -1.5, then we need to count the number of poles and number of zeros. If the number of poles plus number of zeros are odd number, then at -1.5 the root locus is present. If the number of poles and number of zeros are even number, then the root locus will not be present at that particular point. Now, find the breakpoints. To find the breakpoints, breakaway point and break-in point are there. Always the root locus will start from pole and has to end at 0. So 2 poles are present and two zeros will be assuming somewhere else. 2 zeros will be present somewhere else at infinity. We assume that 2 zeros are present at infinity. So the root locus will start from pole and has to end. After finding the breakpoints, now find the angle of asymptotes and centroid. We know how to find the angle of asymptotes and the angle of centroid, and the angle of departure or angle of arrival. All these things we have discussed in the previous class. For over damper system, the K value should lie between 0 to 1. For critical damper system, K should be 1. For under damper system, the K should be greater than 1. There is no undamped nature for this problem. For critically damped system, K equal to 1. For under damped, K is greater than 1. All these points we have discussed in the previous class. Now let us consider with an example. This is an example whether all the 5 parameters we are going to find for this problem. G of S, H of S is the open loop transfer function. We will be drawing the root locus by considering the open loop transfer function. Here the number of poles are 3. Total number of poles are 3. One pole is lying at origin. This is one pole. And 2 more poles are imaginary poles. That is, the imaginary pole locations are -1 plus 1j, -1 minus j. These are all the pole locations. Now to find the centroid is -2 by 3. Angle of asymptotes is 180 by 3, that is 2q plus 1 divided by number of poles minus number of zeros into 180 degrees. Substitute q equal to different values, so that we will be getting it as 60 degrees, 180 degrees, 300 degrees. The angle of asymptotes. And angle of departure. To find angle of departure is 180 minus pi. The pi value is summation of angle of summation of poles minus angle of summation of zeros. Here the angle of summation of poles, here one pole is there, here one more pole is there. 135 plus 90 degrees, that is 225. So angle of departure is 180 degrees minus 225 is equal to minus 45 degrees. And to find whether the system is critically damped in nature or over damped in nature or undamped in nature or under damped in nature, find the characteristic equation of closed loop system. How to convert open loop transfer function to closed loop transfer function. We can convert into open loop transfer function, that is k divided by s into s plus s square plus 2s plus 2. This is the open loop transfer function. To convert this into closed loop transfer function, we need to add the numerator term in the denominator, so that we will be getting it as s cube plus 2s square plus 2s plus k equal to 0. S cube plus 2s square plus 2s plus k equal to 0. Now to find the marginal value of k for the highest power of 3, highest power of s is, if the highest power of s is 3, then product of inner terms minus product of outer terms equal to 0. So k marginal value will be 4. K value lies between 0 to 4, then it's called underdamped system. If k equal to 4, then it's called undamped system. Undamped margin is stable. If k value lies between 0 to 4, it is stable. Let us consider one more example for this. K is divided by s square plus 4. Number of poles are 2. Number of zeros are 1. So 0 is present at origin, and 2 poles are imaginary poles having the pole locations plus 2j and minus 2j. And number of asymptotes will be getting it as 1. Why will be getting it as 1? One pole will be ended at always the root locus starts from pole and has to end at 0. For one pole and 1 0 will be paid, and one more pole will be there. This pole has to end somewhere else. That means somewhere else means it will be assuming a 0 is present at infinity somewhere, and the root locus starts from one pole and has to end at 0, which is present at infinity. So the angle of asymptotes is 1. To find the angle of asymptotes, the formula is 2q plus 1 divided by p minus z into 180 degrees. So we'll be getting it as 180 degrees angle of asymptote. and we can find the s value as minus k by 2 or s is equal to minus plus or minus 2. This will find this. So angle of departure we can find it as angle of summation of poles, angle of summation of zeros, 180 minus pi, where pi is summation of angle of poles minus summation of angle of zeros. So the final angle of departure is 180 degrees. If k equal to 0, then it is called undamped. K lies between 0 to 4, it is called underdamped. K equal to 4, it is called critical damped. If k is greater than 4, it is overdamped. Now let us consider one more example for this. The open loop transfer function g of s h of s equal to k into s plus 2 into s plus 4 divided by s squared plus 2s plus 2. With this example, we are having two poles and two zeros. Two zero locations are minus 2 and minus 4. So minus 2 is at this point is one zero is present at minus 2. One more zero is present at minus 4. And two poles are there. The pole locations are minus 1 plus 1j, minus 1 minus 1j. So always the root locus has to start from pole and has to end at 0. So we need to find, you know that if you want to find a root locus is present at any point, whether a particular point lies on the root locus or not. To the right of that point, if the number of poles and number of zeros are odd, then the root locus will present. So here the breakpoint is minus 2.619. Now how to calculate the breakpoint? Differentiate it with respect to s for this and equate it to 0, so that we will be getting it as some s values. If that s value lies on the root locus, then it is called a breakpoint. Otherwise, it is an invalid breakpoint. Similarly, for this also, same. Just we have interchanged the poles and the zeros. Interchange the poles and zeros. The breakpoint will be same, since minus 2.601. Here it's a break-in point. Here it is a breakaway point. One more problem is g of s h of s equal to k into s plus 1 divided by s square minus 2s plus 2. Here one zero is present and two poles are present. One zero is present at the pole and zero location is minus 1. Pole location is plus 1 plus 1j, minus 1 minus 1j. So the angle of asymptotes is only one, number of asymptotes is 1, since one zero is present. One pole will be ended at 0, 1 0, and one more pole will be assuming that will be ended at 0, which is present at infinity. For k equal to 2, the system is stable. No, one more problem here. The transfer function consists of the only poles at origin. Then the root locus diagram is nothing but angle of asymptotes lines.